And I see that Dr. Eden is on the virtual side of things, and she asked me to introduce our speakers today since I am here. So this is another one of our 2-for-1 faculty presentations so that others in the department, faculty, students, visitors, others, can learn more about the research that our faculty do. So our two speakers today are Dr. Xubo Song and Dr. Ben Orwoll, and I will introduce them, and each of them will speak for about a half hour. So let me begin with Xubo, who is a professor in the department. She also has a joint appointment in the Department of Biomedical Engineering and was previously in the Department of Computer Science and Electrical Engineering that came from the Oregon Graduate Institute. She serves as scientific co-director of the Center for Biomedical Data Science at OHSU and is a distinguished advisor at the Center for Early Cancer Detection at the Knight Cancer Institute. All of her formal training is in electrical engineering. She has a bachelor's degree from Tsinghua University in China and master's and PhD degrees from California Institute of Technology. Her research interests at present focus on the development of machine learning and image analysis algorithms and their applications to various biomedical domains, including cancer, cardiology, ophthalmology, and psychology. And I know that a number of our students know her by her teaching of courses in machine learning, advanced topics in machine learning and image processing. So go ahead, Xubo.
Thank you, Bill, for that introduction. I just gave the same talk yesterday at the Science Day for CBDS yesterday, but that was 15 minutes. So today I'm going to just expand that to add a bit more content for a 30 minutes talk. So overall, I'll be talking about how to use machine learning and to the field of biomedical image computing. And specifically, I will address this question of model generalization. And we all know that the whole point of machine learning to teach machine to learn is not to teach it to memorize things, whatever is in the training data, is to learn from, to apply what it learned from the training set and generalize to new cases and in the test set. So that's the ability of generalization. That's the central theme for machine learning. However, there's always a gap between the training performance and the test performance, and that gap usually arises from several factors. One of them is being the lack of data in general. If you have all the data to train, that will have very little issue with generalization. We have also lack of label data, because labeling data is expensive and time-consuming and takes expertise. And we also have domain-specific data. That means we have a lot of data that could be general. So we have general radiology images, but if we want to talk about breast cancer, we not have enough data for that particular field. So we need domain-specific data. And there's also, we encounter generalization difficulties when we have domain shift. That happens when the data we train on has different distribution from the data that we are applying the model to. And there's also the high cost of especially in the days of foundation models, the high cost associated with training or fine-tuning large foundation models. And we have my group and we have and the projects I'm involved in have addressed these challenges from different perspectives. And I'll give you some examples in terms of dealing with lack of data. Is a lack of data in general, or lack of label data, or lack of domain-specific data. We could use what is called regularization to handle this problem, to alleviate this problem, not completely solve the problem. Regularization basically is a way to inject prior knowledge into the model. Of course, if we have sufficient data, if we have a good way of training the models, we would be able to learn everything we want the model to learn from the data alone. We will have no need to inject anything, but that's never the case, especially when we don't have enough data to train. So if we have certain knowledge about the data, about the model, the behavior, the characteristics we want to have, we might as well build them into the algorithm. So that's a regularization that has been a really important concept in machine learning for many decades, from the start of the field of the machine learning. And then I will also try to address the lack of data by using techniques called by utilizing the unlabeled data. Sure, labeled data is very expensive, but we usually have a lot more data that's unlabeled. Them not having labeled doesn't mean they are not useful. And how to get information out of this unlabeled data, and using, say, combining unsupervised learning with learning through, that's called semi-supervised learning, or supervised learning really is just to learn from the unlabeled data alone. And that's another way of dealing with lack of labeled data specifically. And so I would talk about, there's the strategy of multitask learning. That this means if you have multiple tasks using the same data, and instead of training different models for different tasks, you might as well train one model, same model for this task if they share something in common. So, whatever model parameter representation learned from one task might be useful for the other two. So that helps you condense the model itself, and therefore alleviate the need for data to some extent, and also makes the model more complex and better, more accurate. And there's also the transfer learning, which means you train a model using out-of-domain data, and then fine-tune that model into your domain data. And the foundation models are all about that they're just large data. Models you train on large data, and then you fine-tune them, transfer that into your domain data. And there's also domain shift. That is when your distribution, training and test data has different distribution. That's not something that you can alleviate just by adding more data, because adding more data, they still have distribution. That part does not disappear. So we have to have other methods to deal with domain shift. And examples including domain data augmentation and data normalization. Sometimes we call that harmonization, or there are different names for it, but that's the goal, or explicit method to shift to match these two distributions, actually do the transformation of the distribution themselves. That requires actually modeling distribution themselves. So that's associated with cost. There's cost associated with that too. In terms of the high cost of large model and fine-tuning, and fine-tuning a large model is very expensive. Training a large model is very expensive for sure. But let's say the big tech companies are doing that, and we can use those foundation models to fine-tune them on our own domain data. That part is in our hands. We're out of business for training the foundation models because we don't have the data and the resources and the compute power to do that. But fine-tuning is still something we can manage. However, we are facing with the question of, do we fine-tune the whole model? The model could, Stephen can give you a really good quote on which model has how many parameters, but they're in the level of hundreds of millions to a billion on the billion level. Fine-tune those models is going to be very, very expensive. And we have a way of not do fine-tuning, like tuning all the weights, but only fine-tune a small set of parameters. We call them parametric efficient fine-tuning of foundation models. That small set could be only like 1/1000th of the original set number of parameters, and with comparable performance. Sometimes better, sometimes worse, but mostly comparable, especially given the computational saving. So these are all various techniques, strategies. I can't talk of them all given in the interest of time. I'll just give you some examples on some of the machine learning image processing tasks that we addressed and using these strategies. And I will start with the first strategy called regularization. And in this context, I'll talk about this task of image registration. So what is image registration? Image registration involves two images, and these two images are spatially deformed from each other. And this deformation could be coming from, one patient takes the same imaging, same MRI, across several years apart. It's the same person, but the physiology, the anatomy has changed. So we want to map them spatially to know the spatial correspondences of this image content. These images could be, two images could be the same view taken from two different perspectives. So we want to know how they match each other. And all these registration can allow us to, for downstream tasks such as 3D reconstruction, atlas building, multimodality diffusion, motion tracking, motion correction, and monitoring, quantifying disease progression over time. These are where image registration can be used for. But image registration is a challenging task. Just aligning the spatially is difficult. What makes it even more difficult is sometimes on top of the spatial deformation, we also have intensity distortions. Like these two cases, we know maps here, but even in perfect alignment, their intensities are not the same. And that makes it really hard for us to define the right matching criteria. So when is a good match? How do you measure that when the intensity don't even match? My student, Andrei Marinenko, he's working at NVIDIA right now. He came up with a method called image registration by minimizing residual complexity. I won't get into the details of mathematics of it, but I'll give you a high level intuition, what he's trying to do. So we have two images, I and J. We try to find the transform T to align them. But in alignments, we also introduce a function that's called intensity correction field that accounts for the intensity distortion part of it. And we solve simultaneously the intensity correction with the spatial distortion or spatial transformation. And we have this way of defining objective function that we optimize. And the key is that this intensity, this correction field is not arbitrary image. It has to, we constrain it to be spatially smooth. In other words, it can be regularized by regularizers or operators, which we'll learn from actually as part of the learning process. So to make the long story short, and eventually the final solution is the final transformation that would align these two images to make them registered is the one that would make the registered image, the difference between the two registered images after they register, the difference we call residual image, to have the minimum compression complexity. That means easiest to compress. We can compress that image with the smallest number of parameters, as measured by discrete cosine transform. So this link to from image registration to image compression provides a mathematical insight and clarity, but also provides a way for efficient computation, because we know how to efficiently carry out discrete cosine transform. Just like Fourier transform, we have efficient way of fast Fourier transform. It's really fast. So the implementation, this can be done really quickly too. And these are some examples of how these are registered, retina image with significant intensity distortion as well as spatial distortion, taken 2 years apart, and we were able to register them really well. And we use them to track the motion of the heart from 3D ultrasound. So that tracking would allow us to derive the mechanics of the heart motion, like the strain rate, and torsion, that would provide clinical information, which part of the heart is ischemic, for instance. So this method has also been used by many other researchers to register MRIs, CTs, PET images, retinal images, histology images for tasks such as motion correction, image fusion, atlas building, molecular organization studies, and cancer screening, et cetera, et cetera. So it was well adopted by the research community. Let's see, I probably skipped this. This is to show we also had other further, other algorithm development on image registration, but I will skip those in the interest of time. And now we'll move on to the second strategy that can help to alleviate the generalization gap, which is semi-supervised learning. So this is where we use both labeled data as well as unlabeled data. So the case study here is where we want to segment different cells and cell ultrastructures. These are organelles in the cell. used based on electron microscopy imaging. So inside the cell, there are nucleus, nucleoli, mitochondria, microchromosomes of, they all vary significantly in size, shape, and morphology and texture. And if you look at the images, it's very hard to, it's not an easy segmentation problem. And annotating to generate, manual ground truth segmentation label is very, very, very tedious, costly process. So we only have about less than 1%, 0.1% actually of the data labeled. And so we train our model on those label data, but we're also going to try to use the 99.9% of unlabeled data to improve this model. So there are many technical components that goes into the segmentation process, which I won't talk about, but I would just want to emphasize the fact where unlabeled data can help as well in a semi-supervised learn way. And the way we do that was to use a model called cross-pseudo supervision, in the sense that the gist of it is that we train a model, well, actually we train two models, and using the very small data set that was labeled. And then we use these two models to segment the images that's not annotated. And we use those pseudo label to train each other as if they are teachers for each other. And this is a simple concept, but it really improved the segmentation significantly. Okay, so let me give you some examples of how the segmentation looks like. These are the ground truth with nucleus, and in the middle are the nucleoli. And this panel is ground truth. This is what the model generated. So the precision is pretty high. And this is how the segmentation are showing the fenestration inside the nucleoli so they have biological significances. These are some other examples. The smaller objects are the macrochromosomes and lysosomes that are relevant. These segmentation allow us to further quantify these the density, the spatial locations, proximity, and of these, and shape and morphology of these ultrastructures and cells, so they can lead into biological insights. So here's a video that I think is kind of nice for you to see how the segmentation looks like this is actually the original image. We're going down the 3D stack across this is the segmentation results. The largest one, you can see the cells. The blues one are the nucleus. Yeah, these are the cell boundaries you're seeing. This is a set of a pancreatic cancer patient biopsy sample imaged by EM.
So cool. Sorry, I saw this yesterday. I thought it was so cool.
Yeah, it always helps to visualize it. These are just pulling away the cell, but only see the organelles or the ultrastructures. These are the nucleus and nucleoli. These are adding the mitochondria, microchromosomes, etc. Overlay. So that is a cell segmentation. So I want to move into the third strategy, called multitask learning. In this case, the case of study here is the characterization, classification, and pseudo timing of prostate glands to delineate disease subtypes and predict cancer progression using a combination of histopathology image of H&E stained images, as well as multiplexed immunofluorescence image. So there are two image modalities, and our goal is to so here's how what you can see from a H&E slide. You can see these glands, a little small actually, and it's hard to see, but these are glands that are of Gleason pattern 4. These are glands of Gleason pattern 3. These are the benign glands. our goal is to segment these glands. For instance, every gland has a boundary. This is how they look on the H&E images. This is how they look on the cyclic IF image, which is multiplex immunofluorescence image. And we would like to use them to segment them and to model the progression. So the segment, we have built a pipeline. These are how the, pathologist would only look at the H&E alone and do the annotation, but you can also see the gland differentiation using the cyclic IF on the cyclic IF images. So the rationale is that combining these two is going to give us better segmentation as well as characterization. And so we have built a pipeline to, with the help of collaborators at NVIDIA, that allow us to segment these cells. That's not what this talk is focused on. What I'm talking about here is, given this segmentation, we want to characterize these glands and project them into a latent space, such that in the latent space, we can see where these different glands of different Gleason patterns are sitting. And then hopefully we can chart the progression from CB9 to pattern 3 to pattern 4 to pattern 5. It follows that progression. And do it, so we can use that trajectory to pseudo time, because it's not real time, because we can't really get a biopsy from the same patient multiple times. Even if you do that, you're not sampling the same location or same samples, same cells. So what we're doing here is what's called the concept of pseudo timing, that we only have images at one time instance, not cross time, but in this in the image taken at this one time instance, there are Gleason patterns, there are benign patterns of 3s and 4s and 5s. So we can map those in a pseudo time way. So that's what we're trying to do. So to do that, we need to map these glands that are already segmented into a latent space. And that is representation learning. That is where the challenge is. And so we propose a multitask learning approach, where we train a model that use no label, use the segmentation label, as well as use the text, the classification label, use all three together, learn a representation that allows you to do all three things, the shared representation. That in that way, these different models are constraining each other. So it's in some ways works as a regularizer, and also allow you to learn a more accurate representation. So in the end, this is still ongoing work, as we're still, this is only on 12 patients. And we are now in the process of annotating hundreds of patients. And so we are still building the data, annotating the data, training the model. And this is just very preliminary result, but we can see the benigns in blue, the pattern 3 in green, and the pattern Gleason pattern 4 in orange. So there's transition of the patterns. So we hope with more data and better trained model, we can reveal more insight. So last one, I have 5 minutes, and I will talk about fine-tuning of foundation models. What is foundation model? Foundation model basically is a model, typically is a large model that's trained on a lot of data, or typically from public domain data. And that has learned representation of the data in general, but hopefully some of them can be applied to our domain-specific data, but directly application of that model may not work at the get-go, so we need to fine-tune them with our domain data. So that's the goal. Then we have fine-tuned the foundation model to do a general segmentation foundation model. I mean, some of you have heard of a segment anything model, SAM from Meta. That's a generic foundation model for segmentation. We have fine-tuned that model with the help of our colleagues at NVIDIA, my PhD student Andre included, to segment the glands. So this really shows you how the straightforward zero-shot application of SAM performance is way worse than fine-tuned SAM using this specific set of small annotation. Another thing I want to really point out, this is the last point I'm trying to make today, is that how do we fine-tune these large foundation model in an efficient way? And so my PhD student, Phil Wallace, and he's if you look at the parameter fine-tuning of large models, the leading technology is called low rank approximation. It's called LoRa, and he's a co-inventor on that. The idea of LoRa is that you have these trained weights, pre-trained. This comes with your foundation model. It's already there. And say this weight block has, this matrix has 1,000 by 1,000, so which is a million parameters too. That's already pre-trained. If you do full fine-tuning, you'll be changing all the weights here. So the low rank approximation is to project that to have a side branch where you have two matrices A times B, where A is say 100 times 2 and B is 2 times 1,000. Sorry, A is 1,000 times 2, B is 2 times 1,000. So in the end, A times 2 still give you 1,000 by 1,000, but the actual parameter is only 2,000 plus 2,000 is 4,000. That's only 0.4% of the total number of weights of this blue block. So that's only the weights we tune. So we basically only train these 4,000 weights that by multiplication give you a million numbers. We don't change this, we freeze the pre-trained weight otherwise. So we remember what is learned before from the foundation model, and we add the a million number to it, which really is affected only by changing 4,000 numbers. And that is the orange part is where we learn from our data. And that leads to the fine-tuning of the total weight. So it's much more, it's called parametric efficient. So that's how LoRa works. And then and Phil and I continued working, made improvement to this LoRa paradigm, which saying, of these 4,000 weights, maybe not all 4,000 weights are necessary, need to be changed. If you are given a budget, say we want to allocate which of these 4,000 weights you want to actually change, you give in the budget of 0.4%. And then we allow the algorithm to efficiently figure out, optimize which of the 4,000 needs to be changed through a gating mechanism. And that is called gated LoRa, we call it Gloria. And so that we compared three mechanisms. One is full tuning, tuning all 1 million weight for this layer, or LoRa training, LoRa fine-tuning, or Gloria fine-tuning. And we apply this to both image classification problem and image segmentation problem. For the image classification problem, we use this vision transformer based model trained on ImageNet and using 22 million parameters. That's all we can handle on our GPUs. And you can see the Gloria works better than full fine-tuning. It works better than LoRa, even though it only changes 0.4% of the weights. And same story for segmentation. We still use a vision transformer. We use architecture segmenter. That's not our model, but that exists. And we fine-tune that with LoRa and Gloria, and Gloria still is the best performing. Gloria does not always outperform full fine-tuning. Sometimes full fine-tuning still is better, but Gloria always outperforms LoRa. So that is how the possibility of parameter fine-tuning. So to conclude, what I say, unlabeled data are valuable. We should use them whenever we can. And prior knowledge are valuable. If we have any knowledge, either just intuition, like we prefer the function to be smooth, or physically informed or biologically informed data, we should put them in as a way of regularization. We also learned that domain shift cannot be purely solved by adding more data. There's other elaborate ways has to take place for that to be normalized. Also, there's a debate of generalist versus specialist. Is it better to train the model that learns the general representation of that fine-tune, or is it better to build the best model you can with your specialized data? So that's debatable. So these are lessons we learned, and these are the people involved, and that's funding agencies, and that's my talk.
Actually, can I ask this would probably be too complicated a question, so maybe you just have a quick answer to it. I remember reading a paper about a year ago that found that sometimes these algorithms train on like artifacts in the data. And you know, and I know there's another issue that the images that come out of capture devices from different vendors have different results. You know, how is there any simple answer to how you kind of generalize those sorts of things?
Then that is, there are two ways. We sometimes we explicitly train with artifacts, like you said, so that the artifacts, or we add noise, we deteriorate the image, so that it reflects the true variability of the data from different sites. So then we learn a more robust representation. Or sometimes we just explicitly normalize all the different sites with their variability into a common data, not format, but data representation.
Yeah. Okay, great. I mean, it seems like there's a bunch of sort of real world
That's a very,
considerations
that's a
when
very
when we start to roll this out, you know, outside the lab, so to speak.
That's a very important problem, and we're still
Yeah.
facing that
Yeah.
for any modality, actually.
Yeah. Okay, great. Thanks. Okay, are you ready?
I think so.
Great. Well, I'm going to introduce our second speaker, who, like Xubo, many of you know, Dr. Ben Orwoll, who is a pediatric critical care physician and informaticist here at OHSU. And he's been co-chair of OHSU's Clinical Decision Support Committee since 2019. He's originally trained in medicine, and he got his MD degree from University of California, San Diego in 2010. He did internship and residency in pediatrics, and then did a fellowship in critical care pediatrics, and then got the informatics bug. I remember meeting him actually when he did. And he joined our informatics fellowship in one of the first classes, I can't remember.
16,
second year. And he did very well in his fellowship. He got a master's degree. And then when he finished, he joined the faculty at OHSU, both in critical care pediatrics and informatics. And so he's continued to work in both of those areas, doing a lot of operational work, also teaching in our graduate program. And he's going to talk today about governance of CDS. Ben.
I'm gonna try it. Thanks, Bill. So this is I think, probably a significant departure from a lot of the content of the last talk, but I'll talk about just a lot of maybe real world challenges that we've run into in managing our clinical decision support library at OHSU. And for full disclosure, this is a talk that in very similar, maybe very similar aspects. Let me see if I can get Teams to shut up. Like, right? All right. That I'm presenting along with a couple of my colleagues, Lindsay and Tyler, who are the other co-chairs of our CBS committee at Epic's UGM conference at the end of the month. So that's me. Their pictures aren't on here because they're not presented today, but Tyler and Lindsay are presenting with me later. I don't have any disclosures. I think here we're looking for some learning objectives, but mainly I kind of just want you all to get a sense for what we're trying to do with standardizing our approach to how CDS tools, or specifically alerts in the EHR, are designed and what they look like. So we'll talk a little bit about background challenges, our style guide, and a couple of broad strokes outcomes, and then just what we're up to moving forward. So, you know, we work here at OHSU. This is just some stats about our hospital. It's okay. And we've got four hospitals, 1,000 beds or so, 350,000 admissions, and 21,000 employees, which is probably relevant in terms of who's seeing these things. and about 1.3 million patient visits per year. Just a beautiful picture of our campus. So as far as our clinical decision support committee, we've been doing this since about 2011. I have been participating in the committee probably since 2017 or so, have been a co-chair of the committee since about 2019. We have a group that includes people like me. There's a couple of other physician informaticists on the group. We also have multiple nurse informaticists. We have several Epic analysts, and then we have guests who come and talk about their particular issues. I'm the physician informaticist co-chair. Tyler is our analyst co-chair, and then Lindsay is our nurse co-chair. And just in terms of the scope of our committee, those of you who are familiar with Epic may recognize some of these terms, but essentially these are different types of alerts or different types of decision support that are available in the Epic system. Some of them are, and we'll distinguish a little bit between things that are interruptive, meaning they stop what you're doing and force you to interact with the decision support tool, versus things that are passive, which are more like they're there, maybe you can see them, or maybe you can access them if you want to, but they aren't going to stop you in your tracks from doing what you're doing. And for the most part, these things are interruptive. Well, I shouldn't say that. Maybe half and half are interruptive on this list of things that you're looking at, but more or less they're different flavors of clinical decision support tools that are available in Epic. Mostly what we're going to focus on with this talk is the best practice alerts, which is an Epic speak for basically an alert that pops up or shows itself and tells you what to do, suggests something. We have about 360 of them right now that are shown to users, and it both seems like a lot and not that many. When you think of like the whole scope of patient care, 360 doesn't seem like that many. On the other hand, it feels like a lot when we're trying to manage them all, because there's just not that many of us. So I'll move on to kind of talking about challenges. And this is not all of the challenges that we deal with, but this is some big categories. One is we don't have really good standardization in how we do this. Part of it is related to the third box there, which is that we've had Epic here for 15 years, and there's a lot of legacy things that have sort of vestigial build and vestigial practices, legacy practices that have trailed along as we've upgraded and updated and as things have changed. Similarly, personal preferences and personal practices have affected how we've put together all of these tools. And that has, those things change over time as well, as different people are asking for different things or are doing the build. We have outdated evidence. So, 10 years ago, maybe you were supposed to put everybody on spironolactone for X, and now you're not. Or 10 years, even a few years ago, it was like someone has traveled on a cruise ship. You're supposed to isolate them in a private room and like gown up, right? Because they probably have COVID. And all of these types of things have to be like fair. At least don't touch them for their norovirus now or whatever. But these are things that like are difficult to keep up with. Lack of ownership is a big one too, because actually it turns out, there's a lot of flux in the OHSU community. And even if you had someone who was a big champion or owner of some process early on in your development, that person either may not care anymore or probably isn't at OHSU anymore 5 years later, honestly, when it comes to both the clinician workforce as well as the sort of administrative workforce. On top of that, we have limited resources and limited time to do all of this stuff. So part of what we embarked on was we said, gosh, we really need to have a better way to go about this. And this is, we're always trying to come up with new ways to improve the system that we use. But the idea was, okay, we need a more concise way, or not concise, a more well circumscribed way to do development and updating of our clinical decision support tools. And so I think Lindsay, who's the other co-chair, was a big proponent of this when she joined the committee a couple of years ago, and I thought it was also a great idea. And so we did this in part because also with some of these challenges that that I showed, and with sort of the growth of OHSU's informatics reach, we now are at more and more hospitals. There's legacy. There's all sorts of things that are happening. Our ability to maintain a consistent approach is less and less feasible because we have to actually farm out the work to more and more people. And so you kind of need a document. You kind of need a policy, right? So this is why we started to develop this approach. And we've tried to take a pragmatic approach also, just that we can't be perfect, and so we want to be better. And so that's one of the guiding themes that we use in this process. We also, Bill recognized this guy, but we actually took quite a bit of insights from previous leaders in the CDS space. And Adam Wright, who's one of our graduates here from DMICE, who now is at Vanderbilt, has done a lot of work and presented and published on strategies around how do you make your clinical decision support work better, but also how can you design it in a way that's more appealing and useful to the end users. So I just wanted to call Adam out because I've leaned on his, and I'll give you all a chance to look at this for a second. If you want to use your phone and pull it up, it's on a OneDrive that's accessible, just because I'm not going to show the whole style guide right now. But I'll go through some of the top points. But really, we wanted to create a document that we could say, all right, analyst X, we're updating this alert. Can you take a look at it? Can you now, look at the style guide, update different things, and make changes as you see fit in order to adhere to the style guide? And so as far as the content of the style guide, and you can read through it, and the one thing to know about the style guide is a lot of it is just this is a starting point, and we are trying to have something that we can then iterate upon. You have to have something. And so when we've talked to people about this, they're like, well, did you have people who were trained in design theories, and did you do all this type of kind of more rigorous development of exactly how this should work? And I would say, no, we didn't. I wish I could say that we did. On the other hand, we don't have those kind of resources, and but we do have a lot of experience built up amongst us, and we do have some things to draw upon, such as other organizations and at least some amount of CDS published data. And so we started off with what you see, things like, part of it is also you want the users to have a consistent experience. You want, when someone has an alert come up in front of them, you want them to know where to look for the relevant information that they need in order to act upon that alert. And so, you want them to know what's, or have, you know, not even like explicitly in their heads, but subconsciously maybe, this is where I'm going to see these elements. This is what it means when I click this, or this is what it means when I click this other thing. And so things like standardization of the header style and the font. There's, and these are, again, this is like a little bit of Epic nomenclature, Epic speak, but things like when you have, and I'll show you examples of what I mean by this in a second, but BPAs or these alerts, they have various things that you can do, right? They have some text, they may have some images, they may have some links, so you can click on links. They may have an action that you can take directly from within the alert or the CDS tool. They also may have buttons that say things like, delay this, or this isn't the right button for me, or this isn't the right alert for me, or not applicable, or some other comment. And we want to have these types of things be relatively consistent. So one thing that we found a lot in our old system is we have these, what I call informational alerts, which I'll show you one of, which we improved but haven't gotten rid of. Sometimes people just want you to see some information, like the chart's full of information, right? But this piece of information people think is so important, it must be flashed in front of you, saying, look at me. And the problem with that, among other things, is that everybody's got their pet piece of information that they think is so important that you have to see. But really, you know, you've got a whole patient in front of you, and you may or may not think that that's important. So we've had to deal with a lot of those things. And then I think we've also looked at things like the triggering action. And this triggering action may not mean a lot to you if you're not a frequent user of Epic, but essentially you can do different types of things in Epic, like write an order, open the patient's chart, file some piece of vital sign data, send a message. Any of these types of actions can potentially be the triggering point for the logic to be executed of an alert. So we want to really look closely at what those triggering actions are. And in our style guide, we really have tried to limit the cases for the most hated of all triggering actions, which is the open chart triggering action, meaning anytime you interact with this patient's chart, you're going to see the alert, which is like, but yet so many of our alerts have that triggering action, in part because if you want to make sure everybody sees it, well, that's the best way to make sure of it, because you can't count on anyone to do any particular action. So, and then lastly, a key piece of this is that we have, and for several years had this, but we sort of instantiated in our style guide, a custom survey link in our BPAs that flows to a Qualtrics survey that sort of carries with it some metadata about what the user was doing, what they were, what patient they were looking at, et cetera, and then allows them to just very quickly submit some feedback that we then get. So when do we use the style guide? We're using it for any time that we get a new BPA that we're trying to do. We do it anytime that we're essentially, whenever we touch a BPA, we're trying to say, all right, well, we needed to update some logic in this thing, but at the same time, let's just revamp the style guide because this is an opportunity for us to touch it. So this is a little bit busy. Hopefully you can see things that are key here, but this was one of those informational alerts. And what I'm showing here is things on our style guide that we're trying to improve. So this was an alert that essentially pops up for people in the emergency department that says, hey, this patient is on the ketogenic diet, which means they should not get dextrose generally or glucose. Make sure that even though this patient's blood glucose might look low to you, actually it might be fine. Can you take a look at this table and not give them dextrose? And when we first started, like, it's kind of busy. There's some long text. Things are small, and it also has this dismiss button down here that I'll talk about, but essentially we are taking some of these elements and trying to tighten them up, not allow people to use this dismiss button. And you may see in the style guide that we discourage the use of the dismiss button. And that's because Epic, in fact, people have this muscle memory. They know when the chart opens, something's going to pop up. And this is like a phenomenon in computer science when they're hovering over where the dismiss button is going to appear so they can click it, right? Before they even see anything. And that's a sign that probably this is not the right time for them to see the alert. But B, in Epic's functionality, the dismiss button robs us of any ability to control when that alert shows up again. For example, you can see that I have buttons here that say silence this for me for a period of time. If you hit dismiss, it will not be able to silence it for you. So the next time you open the chart, it will still show, even if you've sort of seen it, it'll still show because you're hitting dismiss. And users don't know this, most users at least. They just are like, why does this thing keep popping up? So we're trying to make it so that it's easier to interact with these things. And I mean, partly this looks better because it doesn't have boxes all over the place, but highlighting for you just that, like, we're trying to put a little bit more imperative text in the header. We're trying to make it a little bit less wordy. One key, and this was taken from various places, but also from work that Adam has done, is like, make sure you're putting something in the alert that indicates to people why the alert has fired, and not even just generically why, but actually show them the element of data that is driving it, so that if they then think it's wrong or want to know why it's there, they could actually go and just like take it out. We've removed the dismiss button, and now you basically have to choose one of these things. And just by removing the dismiss button on some of our alerts, we've seen the firing rates drop by like 90%, because by that people don't want to see it over and over again. They just want to be able to silence it. And so I'll show you another example. This was one of the influenza vaccine alerts are some of the highest rates of firing in our system. And a nurse would see this, and it says, influenza screen was marked as unable to assess or ICU care if the patient is transferred to the ICU, blah, 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 please complete the screening, blah, 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 right? You also, these buttons are not super clear, and then just inconsistent formatting, very busy. You see the dismiss button down there. People just roll through this. They're in the middle of doing their work. They can't read this whole paragraph of stuff. And I'm not saying that this is perfect, but I think we have attempted to pare things down, remove things like the dismiss button, and just say, okay, you don't want to do it right now, you can defer it, you can indicate that you're not the right person, you can put some sort of other, it's much cleaner. And you can also see this is where these feedback links go, and that's like we have the feedback links for years have now just come directly to my in-basket, which I did on purpose. And you would be surprised that very few people just rant in them, and almost everyone who actually takes the time to click on a feedback link has something useful to say. And I need to count them up, but I've probably gotten, I don't know, 100 to 150 responses maybe over the 3 or 4 years that that's been in place, which is not that crazy, and maybe get 5 to 7 a week. So maybe that's, you know, and the more BPAs that we put this link into, of course, the more feedback that I get. But it has also identified, right? How do you identify alerts that aren't working if you don't hear from people that are using them? And so this is, people just aren't going to like see one alert like this and call up the help desk line and say, hey, I see this pop up and it's not really the right patient. They're too busy for that. They're just going to dismiss it and move on. And the nice thing is this includes all the information that we as analysts need to see to understand exactly the conditions that this alert fired in. So it's really useful. So I want to just finish by showing you a couple of our outcomes. So this is not meant to be only because of the style guide, but I do want to show you that, and the resolution is not coming out perfectly, but on the far left, you see January of 2020. And then in the far lower right is the end of the year, 2023. And this is overall interruptive alert rates here at OHSU. The big spike you see there is COVID. We went crazy with the COVID alerts. But we've been trying to take just a strategy of reducing unnecessary interruptive alerts through things like the style guide updates, through things like moving certain things to non-interruptive status. And I think just the more I look at this, the more I see that we're just like hammering this rate down and trying to reduce the number of alerts that our users are seeing to something where instead of seeing these as an annoyance that they just need to get rid of, they might actually start seeing them as something that is useful in helping them make decisions, which is the whole idea. Support you. Right? And then this just is another example of what we did specifically with the influenza alerts. This was last flu season, and this is this flu season, and this is when the summer when we have it turned off. But you know, we were able to take these flu alerts particularly and reduce it from something in the 30,000 alerts per this is by month per month down to less than 10,000 per month. And it's not like we have a fifth of the patients. We have the same number of patients and our flu vaccination rates are approximately the same, but we just don't need to show these alerts quite so much. So we've only done about 10% of our BPAs updated for this style guide, so we've got a lot of work to do. Unfortunately, we don't really get paid to do this very much. Like, I get some time that is not explicitly for the CDS committee, and spend a lot of my time on the CDS committee. But it's important work, I think, in our minds, and so we want to keep doing it, and I think it's impactful. And but I think our lessons are, we're trying to do this piece by piece. It's hard. Every time that we look at an alert, it's a unique situation, and it's a lot of work to manage one of these CDS libraries. And so I think as we move forward, we're trying to just continue evaluating our BPAs. We're trying to use a new functionality that is not quite available, but something where one of the things we struggle with a lot, and I know I have just 1 minute, but something we struggle with a lot is actually figuring out whether a BPA is working. It sounds bad to say that when you're like, how this whole thing, but like, how do you figure out that something's actually working? Epic has been introducing some improvements in our ability to indicate specific outcomes that are indicators of whether a BPA worked. Because you don't actually know whether, even if someone looked at your BPA and then took an action later, it's hard to connect those things up. And so that's been a challenge. Continuing to work on our style guide and iterate on it, and then continuing to get more feedback from users and actually try to establish a better workflow for the feedback. So anyway, thanks for your attention. Happy to take a couple questions. Thanks to my whole CDS committee.
Do you think some hospital or clinic systems are forward enough to hire and compensate appropriately people who do this part-time or full-time?
You know, I don't know exactly how every place allocates their resources for CDS specifically. I think there are definitely different types of models around kind of clinical informatics workforce at different places. Some places, and OHSU actually has a pretty robust set of people who do have some of their time allocated for work on clinical informatics. I think clinical decision support and these alerts specifically maybe don't get quite as much attention here. On the other hand, I can't tell you exactly how much people are getting at other places. We're presenting at XGM alongside a group from Stanford, and I would say they have a system, but their system also seems like equally as disorganized or equally as sort of federated and distributed as ours. So. Yes.
I think I have a style guide as well, or
Yeah.
recommendations.
Not really. Nothing that we've been able to really clearly identify or get out of them. I mean, there are different Epic produced alerts, like things that you kind of out of the box. They'll just like, here's one that we made. Do you want to use it? And they're kind of all over the place. And they've, yeah, they're not great, in my opinion also, but you know, Epic does a better job than a lot of EHR companies, but they also struggle to channel the needs of the end users really accurately. And their like idealistic way that a hospital or a healthcare system operates just isn't reflected in real life in many ways. So, but anyway, thanks for coming.
So,
People,
what's that?
people.
Oh, yeah, people should sign in if you don't